So it's wonderful to welcome all of you to the Lunar and Planetary Laboratory. I'm Mark Marley, the chair of the Department of Planetary Science and the director of the Lunar and Planetary Lab. The LPL was founded by Gerard Kuiper in 1960, who came to Arizona to found the first institution worldwide to focus entirely on the study of the planets of our solar system. The academic program, the graduate program, was then added in 1973 with the goal of providing an academic opportunity for graduate students to learn about planetary science that met the same high standards of the original Lunar and Planetary Lab. And Kuiper collaborated closely with Professor Blitzer in the original founding of the academic department and LPL in the 1960s and 70s. Since the original students came with Kuiper to Arizona when the lab was founded, we've gone on to educate hundreds of graduate students who have gotten degrees in planetary, their PhDs in planetary science from LPL and the Department of Planetary Science. Given all this history, it's an honor that we are able to recognize today one of our own faculty for the Blitzer Graduate Teaching Award. I want to say that when I was a graduate student here at LPL, I took a course from Professor Blitzer in the orbital dynamics of satellites. And so I can attest directly that he was a very insightful teacher. He was great at explaining complicated subjects in an understandable way. And I learned a lot about how satellites and bodies orbiting other bodies responded to perturbations or changes to the gravitational field that influenced their orbits. It turned out that I actually used that knowledge when I worked on my own PhD thesis here when we were looking at how the rings of Saturn could be influenced by changes in the planet itself. As Saturn rings like a bell, the gravitational changes alter the orbits of ring particles to produce features we can actually see in the rings. It turned out the Cassini spacecraft confirmed this hypothesis, and there's now a whole field that I no longer participate in, but that's since blossomed, called chronoseismology, or the study of Saturn's seismology. And it's really, Professor Blitzer deserves an important role in that he conveyed the knowledge that helped establish this whole new field. So given all of that, to say a little bit more about the history and the award itself, I'm pleased to introduce our Dean of the College of Science, Professor and Dr. Carmela Garzion.
So it's a real privilege to be able to welcome you all here today, and also to thank Mimi and Charles Blitzer for creating this award and this lecture. This award is funded through the Professor Leon and Pauline Blitzer Teaching Award Fund, held at the Jewish Community Foundation of Southern Arizona. And the award was established by the Blitzer children, Mimi and Charles, to honor the memory of their parents. The award has cycled through multiple departments, physics, atmospheric science, astronomy, and planetary science, which spans the impact that Leon Blitzer had during his career at the University of Arizona. And I'd like to just touch on some aspects of the bio for Leon and his wife, and that to say Leon and Pauline, and just to thank Mimi and Charles for providing some of these tidbits to fill in some of the history. So Professor Blitzer began his nearly 70 years, count that, 70 years with the U of A physics department as an undergraduate, earning a BS and MS in 1938 and 1939. And he was awarded his PhD from Caltech in 1943 before coming back here as an assistant professor in 1946. And so as one of the few faculty in physics to be pursuing research at the time, his work focused on spectroscopy, astrophysics, and celestial mechanics. And he received one of the first grants to the Department of Physics. And in 1949, at the age of only 33, for those of you with a PhD, count that time since PhD, he became the youngest full professor on campus. So pretty remarkable early career. And so Dr. Blitzer was devoted to both graduate and undergraduate teaching and received many accolades for his remarkable skills. He was also the driving force in starting the PhD program in the department. Dr. Blitzer personified even the most modern ideal professor in his dedication to teaching, research, and service, which are all still components that we very much pride ourselves on. So throughout his career, his extensive activities beyond the academy were also reflected in his desire to help the local community, something we also still focus our attention and goals on. And after retiring in 1986, he remained active in the department for years, attending faculty meetings, advising undergraduates, and mentoring university physics teachers in support of continuing a legacy of strong teaching. Pauline Blitzer came to the university in the 1930s and met Leon here. And they married in 1942. And after receiving her BA in education in 1940, she taught elementary school until she retired in the early 1950s. She was also an important part of the Leon Blitzer legacy at the University of Arizona, and she was well known to students and faculty as the hostess of the Blitzer home. And so for 50 years, Pauline was active in many activities that supported the community, including raising funds for Hadassah, for civil rights organizations, and for fighting cystic fibrosis, heart disease. And so clearly, both Pauline and Leon were really dedicated to many aspects of our community on campus and beyond campus. The University of Arizona is exceptionally strong in the sciences today, and I just want to reflect on these bios as an important component of our history and the legacy of early pioneers like Leon Blitzer, who really established research as a major strength at the University of Arizona. And so he cared a great deal about research, but also teaching and engaging students in that research experience, both in the classroom and in his research group. And so we have a legacy of recruiting amazing faculty, including Ilaria, which you'll hear from today. And these are faculty who come here for a lifelong career. They come because we have amazing resources, we support research, and we simply do incredible things. We do the types of things that no one has tried before, and we succeed at them. And so I know we're experiencing uncertain financial and leadership challenges right now, but I just want to take this special occasion to really celebrate our amazing faculty like Ilaria, and just to share the College of Science's steadfast commitment to continue this incredible legacy that was started through early pioneers like Leon Blitzer. And so thank you for joining us today. Let's celebrate this amazing moment and look forward to hearing from Ilaria.
Well, indeed, let me call up Professor Pascucci. It's my pleasure to introduce Ilaria. She has received her PhD from the University of Heidelberg in 2004, where she worked on massive star formation. After her graduation, she held several roles, including working as staff astronomer at the Space Telescope Science Institute, where the Hubble Space Telescope at the time, and now Hubble and James Webb Space Telescope, are controlled from and targeted. She joined LPL in 2011 and became a full professor in 2022. She has published over 150 papers and received a number of recognitions and awards, including being named as a fellow of the American Astronomical Society in 2022. At LPL, she has taught many of our graduate and undergraduate courses and deserves special recognition for developing and teaching Planetary Science Astronomy 450-550, a joint undergraduate-graduate class that focuses on the origin of the solar system and other planetary systems. She's advised 8 graduate students, 15 undergraduate students, and 6 postdocs. So welcome, Ilaria. And if I can call up Charles and Mimi Blitzer. They are the children of Professor Leon and Pauline Blitzer and will present the award.
Can you hear me okay?
Yes.
Okay. 5 years since we did this last, and we've all survived the pandemic and many other adventures and misadventures. And above all, I'm grateful today for that. We have a lot to celebrate. And a couple of things I wanted to point out. Of course, Ilaria, the current winner and a wonderful winner. And we look forward to hearing what she has to say. We have a number of past awardees here, beginning with number 1, Johnny Shea, sitting somewhere over there. And thank you for coming. Carmela, in her remarks, talked about the physics department in the early days. I remember when I was small enough, the Stewart Observatory really looked tall. But I first remember about the physics department in the 50s. There were 3 and only 3 professors. Maybe there's a 4th. 2 of them did nothing but teach. One was the chair, a very interesting guy named Earl Warner. My father actually wrote about in the context of how Arizona treated pacifists during World War II. And my dad was the only one who did any research. And then later in the 50s, the university began to expand its focus on science. And the leader of that initially was someone named Harville. He has a building here. And Harville recruited, among others, the new head of physics, who recruited its generation, Al Weaver, who became vice president, dean of science, or whatever. And the 2 founders of the what's now hydrology and Astro out of Iowa State. And that all started to happen. It's a different place. And we all stand on the shoulders of giants. As you know, there are 4 departments that share the award: physics, astronomy, the 2 original departments, LPL, and hydrology, atmospheric sciences. And it'd be remiss, I remember, and we should celebrate also today and remember the wonderful life of Thomas Meissner, who was the chair of that department and who's most sadly no longer with us. So a lot to celebrate, memories to celebrate. And without further ado, Mimi? Oh.
Just a couple of words. First, all those stories that Charles already said, I'm not going to repeat. I grew up on this campus. My father picked up all my friends in the neighborhood and drove us to Sam Hughes or to Mansfield Junior High or to Tucson High every morning. But we lived on this campus, and it felt like home all the time. And that was very exciting. I think I wanted to bring up one thing about my father being 33 years old and a full professor. That was, that to me is way before I got any kind of rank like that. I think I was still a postdoc at that age. But if you asked him really why was he promoted to full professor, is that this university had no money. And they weren't going to be able to raise his salary, but they could promote him. I mean, they felt that that was a better honor. And in some ways, maybe so, maybe so. The other thing I don't want to forget or be remiss about is this is the first time we've had Zoom, people participating in a different way. Obviously, I guess this is a plus from COVID. I know a couple of our close family friends in different parts of the US have Zoomed in today. And I want to welcome them, and I'm very excited that they could join us as well. Without further ado, we would like to present you with your awards first and then hear your talk. And so we do have, I guess it's stuck in here very tightly. I'm not going to take it out for you. plaque
Thank you very
that
much.
we'll take a picture afterwards. Before, I was excited to have another woman scientist participating in such a good award and especially recognizing teaching. And an honorarium check will be coming to you shortly. One other thing we should say is that as it's called, it's an Excellence in Teaching Award. Many of us in the sciences are awarded for our research and the grants we bring in and the like. But as was mentioned earlier, my father, I think, was recognized pretty well as a master teacher and educator. And I think we don't do enough in the field to recognize that. And that's why we're so excited. Thank you.
Thank you very much.
And thank you so much to Charles and Mimi for the presentation. And now we'll get spun up to hear the talk from Professor Pascucci. And her title is going to be From Planet-Forming Disks to Exoplanets, Reconstructing the Paths to Habitable Worlds. And if you were going to, as Mimi said, it's on Zoom. If you have a question online, please enter it into the Q&A chat box, and we'll read it out after the conclusion of the lecture. So if you're all set to go, I'll turn it over to Ilaria.
So can you hear me well? Okay, great. So thank you very much for the introduction, Mark, and also thank you very much for the award. I am really honored to receive it. As I shared with some of you already, I grew up in a family where really it was starting only from my generation that there became the possibility to study beyond high school. So I was one of the lucky ones, the first one in my family to attend college. And I can tell you, I was always reminded that that was a privilege. Also in my family, there was always a lot of emphasis in education and also the important role that teachers have in our society. And this is why I believe when the opportunity came for me to decide between staying at the Space Telescope Science Institute as an assistant astronomer, and essentially support the Great Hubble Space Telescope, or come to the University of Arizona as a faculty and also have the opportunity to teach, I decided to come here. So again, this award is important for me, and it's also important for my parents, who I believe are attending on Zoom. So now let's get started with the lecture. And I want to start by showing to you this beautiful picture of the night sky from the European Southern Observatory, which I had the privilege to go to and use this telescope when I was a graduate student in Germany. But I have to tell you what I remember most from that is really this beautiful sky. And is in fact by looking at that sky and many other beautiful night skies that many past generations before us were asking that profound question: are we alone in the universe? It is amazing that today technologies have advanced so much that we are getting closer and closer to answer that question. That is exciting and at the same time daunting. And it has been recognized by the astronomical as well as the planetary science community that once we detect those potentially habitable planets, we need to place them into context. And we need to understand also how those planets have formed. So today's lecture, it's about planet formation. And I will broaden it a bit more to talk not only about small planets form, but also how gaseous planets like Jupiter form. So we start with this schematic picture of planet formation with different stages. And this is one of the sketches that I use actually often in my class. We start here from the top, where what is highlighted is a patch of molecular cloud. So think about it as gas and smoke-like particles, where essentially gravity wins over other forces, okay, like pressure. So because gravity wins, it means that this cloud starts to contract. And while contracting, it starts to spin faster and change shape into, we move to the second part, in this flattened structure where the star forms at its center and the gas and the smoke-like particle continue to circle around the star. And these are the building blocks of the planets. I said that when the cloud starts to contract, it also spins faster. And this is because of a physics law that we learn in high school. And this is the conservation of angular momentum. So I want to show you a parallel in this video of how essentially that works. We are used to this law. Okay, I knew. Let me see. Okay. All right, so I tested it before and now it doesn't work. But I can tell you what happens. I cannot demonstrate it, but if you, as the skater pulls in her arms, essentially what happens is that it spins faster. That is the conservation of angular momentum, and that is also the same physics law that leads to this faster motion of the cloud and flattened structure after. All right, then when we move here to this third part of the sketch, what is highlighted is that these planet building blocks will have different composition. And that is because the main heating source in this circumstellar disk is the central star. So close to the star, it's going to be hot, and further out from the star, it's going to be colder. One of the main constituents, gaseous constituents in this planet-forming disk is water vapor, which means that beyond a certain distance from the star, it's going to be cool enough for water vapor to condense onto ice. And so beyond that location, which is called the snow line, the building blocks will be a mixture of rock and ice. And inside the snow line, the building blocks will be mostly bare rocks. So we can have a parallel of this snow line when we look at the Catalina mountain in one of the rare occasions in which it's cold enough to have snow. So here is the Catalina mountain, and this is the snow line in the Catalina mountain. Essentially, above, it's cold enough to have this mixture of ice and rocks, and below, it's the usual bare rocks of the desert. All right, so where was the snow line in our solar system? So here is a schematic picture of the sun and the planets in our solar system. Only sizes are to scale, not distances. And thanks to the observation of asteroids in our solar system, we know that the snow line during the assembly of the asteroid and planets was at this location between Mars and Jupiter. So here is the Catalina snow line now tilted and moved in that direction. So it means that beyond the snow line, again, we had ice and rocks to build our planets, and inside only bare rocks. And so to first order, this concept of the snow line explains the distinction between the large gaseous and icy planets in the outer part of the solar system and the small rocky planets in the inner part of the solar system. Before I move forward, you can see here that there is also Pluto, which is called a dwarf planet, but probably many of you have heard that at least as of last Friday, Pluto is the official planet of Arizona. So for all those kids, like my nephew, who love Pluto, when they come here, they can call it a planet, and we've not. Okay? So now, moving forward, from this stage where we looked at the building blocks of these planets to the formation of the planets themselves, this smoke-like particle that we have initially in the cloud, they have to make an amazing journey. They have to grow by 12 orders of magnitude to become the cores of the planets. So when we do observations and we try to piece together how planets form, we are unable to look at all these different stages. When we look at the disk around young stars, we are essentially sensitive to dust up to the size of pebbles that you would find in the beach. So small indeed when you consider how large is a planet. But then we have also the opportunity to look at the outcome of planet formation. So this amazing diversity of planets around other stars, the exoplanets that have been discovered so far. So one unique approach that we have taken in my group is to link the observations of the early stages of planet formation in these circumstellar disks with the final outcome of planet formation, the exoplanets that have been discovered recently. So today I want to tell you about a few results from my group that have made that connection. So here is my outline. First of all, I'm going to tell you briefly about which data we can use to learn about circumstellar disks and exoplanets. Then I'm briefly going to mention what we are learning about how giant planets form. Then I will go into how smaller planets like Earth form. And then finally, I'm going to address this question: how common are Earth-sized planets? And that's an important question for upcoming missions that are going to detect small planets like Earth and potentially also biosignatures on those planets. So here is a bit more complex picture of a star with a planet forming disks. And the only thing I want you to take away from this picture is that it's complex, okay? So we have grains of different sizes, perhaps the planets, many different molecules. And the bottom line is that we need to use different instruments and different techniques if we want to take a clear picture of these objects. So we want to observe from the optical wavelengths. These are some of the telescopes that we are using for our research, to the infrared wavelengths, out to the millimeter and centimeter wavelengths. So for the purpose of today's talk, I'm going to focus on just two wavelengths regime. I'm going to talk about the infrared wavelengths with the Spitzer Space Telescope first, and now you have heard with the James Webb Space Telescope, and the millimeter and centimeter radio wavelengths with the Atacama Large Millimeter Array. So this is a sketch of the electromagnetic spectrum. And again, it is to emphasize that with these telescopes, we have access to wavelengths that are not accessible in the visible. So we have additional information that we can learn by using these telescopes. So James Webb infrared and ALMA radio wavelengths. So let's see a bit how these circumstellar disks look like at these different wavelengths. So here it is a picture of the Atacama Large Millimeter Array. This is an amazing facility of more than 50 12-meter antennas that work together to take incredible, sharp, sensitive pictures of different objects in the sky. So let's see how circumstellar disks look like at these wavelengths. So this is a beautiful gallery of disks around young stars observed with the Atacama Large Millimeter Array. The star is at the center of each of these objects and is not visible, but what is mostly visible here is the emission from pebble-sized grains circling around the star. So at radio wavelengths with ALMA, we probe these icy pebbles in the outer part of the solar system, beyond the snow line. And what you notice here is that this pebble distribution, if you want, is not smooth, right? There are structures, and many of these structures can be linked to planets in formation. By the way, this is a beautiful gallery taken by Fen Long, who is a Hubble fellow working here at the LPL, my group. So now at infrared wavelengths with the James Webb Space Telescope, now I'm going to show you a different technique, spectroscopy, which I know also Professor Blitzen were pioneering here at the University of Arizona. You will see that the disk around the young stars using spectroscopy looks very different. We are probing a different also regime. And so with spectroscopy, by splitting finely the emission at different wavelengths, we can probe molecules, the gaseous species that are present in these disks. So this is a new James Webb spectrum of a disk around the young stars, a paper led by my graduate student, Cheng-Yan She. And what you see here, all these lines are the fingerprints of molecules in the inner part of this disk, so inside the snow line, okay? And in particular, you see water vapor very dominant in this type of spectrum, okay? So we will see how we can connect the ALMA probing icy pebbles beyond the snow line and JWST probing water vapor inside the snow line to learn about planet formation. All right, now the exoplanets, the outcome of planet formation. This is a nice animation that shows the number of detected exoplanets as a function of the discovery. And as the movie goes on, you will see, so this 51 PEG-B, the first planet around the Sun-like star. And then as the movie goes on, you will see that there are more and more exoplanets discovered. And when new NASA missions are launched, you will see that these numbers increase very quickly. So by the end of this animation, this is the Kepler NASA mission, and you can see how the numbers of exoplanets is really growing fast. So by the end of this animation, you see there are more than 5,000 exoplanets, and this was 22, so the number has grown, confirmed around other stars. I like this animation because it also shows that there are different techniques that can be used to detect exoplanets. But two of them are those that have discovered at the moment the majority of the exoplanets. So you can look at this red curve, which is radial velocity technique, and then here in green, the transit technique. I will show you two animations to give you an idea of how we detect these planets with these techniques. But the important message is that we have not seen the majority of the exoplanets that we know of. We have not been able to take a picture of those planets, but we know of them because of the indirect effect that a planet has on the other stars. So both of these techniques are so-called indirect techniques to detect exoplanets. So we study the property of the star, and by monitoring the property of the star, we know that there is to be a planet around. So let me show you how that works. So first of all, here is the radial velocity technique. So because of the presence of a planet, the star also moves around the center of mass of the system, which means that if we have a telescope to measure how the photospheric lines of the star moves as the star approaches us or goes away from us, we can infer the presence of another object allowing that movement. The transit technique is a little simpler. So here we monitor the brightness of the star with time. And if there is a planet passing in front of the star will dim, okay? And so by that dimming, we are able to learn about the presence of a planet. And these are some of the surveys that we have used in my group to learn about the intrinsic frequency of these exoplanets. Now, even though we have not directly detected this planet, we couldn't take a picture of the planet, we still learn a lot about their properties. So this is a plot showing the outcome of Kepler NASA mission. Each dot here is an exoplanet for which we know its size and its orbital period. Essentially, how large is the planet and how long it takes for the planet to complete a full orbit around its star. For reference, you can see here the size of Jupiter, Neptune, and Earth. And to place our solar system again into context, we can see that here is the orbital period of Mercury, and there is the orbital period of Earth. So we know a lot about the population of exoplanets relatively close to the star. Now, one other important thing to realize is that this survey, as well as all the other exoplanet survey, they come with some biases. It's obviously easier to detect a large, massive planet close to the star than a small planet like Earth, especially further out. And so when you want to learn about the intrinsic frequency of planets, how frequent really are these planets, you need to account for the biases. And this is a lot of the work we have done here in my group at the University of Arizona. So my postdoc, my former postdoc, Thijs Mulders, now a professor at the University of Adolfo Ibáñez in Chile, developed this very nice tool, the Exoplanet Population Observation Simulator, which enables you to calculate the intrinsic frequency of exoplanets. And so this was also supported by our former large astrobiology grants, the Earth in Other Solar Systems. I want to mention this is also a very nice teaching tool. So you can, it's written in Python, so you can download it for your class and then calculate yourself the occurrence of different planets. So let me demonstrate this now. So this is again the same plot of planet radius as a function of orbital period. Each dot is a candidate exoplanet observed with the transit technique with Kepler. And now it's color-coded by the completeness. In other words, if the dot is yellow, it means that you have 100% probability of detecting that planet. But if the dot is blue, then the probability is much lower. And so you need to take that fold in your calculation if you want to understand how frequent are planets. So what you can do with this tool is that you can draw boxes in different parts of the region and ask the question, how frequent are those type of planets? So for simplicity today, I'm going to draw just two boxes, the giant planets, planets that are as large as Jupiter, and then smaller planets like sub-Neptunes, just to show you the difference. So let's look at the giant planets. They are up there. And if you use EPOS, you will see that the frequency is 10%. So 1 out of 10 sun-like stars will have this type of planets in this region. Now, what about the smaller planets, the sub-Neptunes? Well, wow, now the frequency is 100%, meaning that all of the stars would have this type of planet. So now let's get to the question, how do giant planets form? So there are two main formation scenarios out there. The first one is highlighted here, is essentially similar, relatively similar to the star and disk formation scenario that I've shown you before. So essentially is also called the top-down model, because the idea is that there is a clump in part of the outer part of the disk that becomes gravitationally unstable. Essentially, gravity wins over other forces again, and that is essentially the clump that will form your gaseous planet. The core of the giant planet in this case is formed after, by accreting the material, the dust from the disk. So again, this is the top-down model. The other model is instead the bottom-up model, because you need to start by growing your submicron grains up to the scale of the cores of the giant planets, and then only then you will form you can accrete the atmosphere from the disk. So these two different models have very different predictions on the type of masses of planets that you will form, as well as the distances of these planets from the star. And so one thing that we have done with my former graduate student, Rachel Fernandez, now presidential fellow at Penn State, was to look at the distribution of the giant planet as a function of distance from the star. Again, the true, the intrinsic, unbiased distribution of giant planets. And so this is a plot from the paper where we compare what we have from the transit survey, which is in pink, with what we have from the radial velocity survey, which extends at larger orbital periods, so larger distances from the star. And when we saw this plot, we were really surprised and happy, because we noticed that there is this kind of turnover in the distribution of the giant planets. In other words, the frequency of giant planets does not always increase as you move far away from the star, but at some point it kind of drops. And the interesting part was where that happens. So that happens between 2 to 3 times, 2 to 3 astronomical units, so 2 to 3 times farther away than Earth is from the sun. And that's very close to the location of the snow line in our solar system. So again, now linking what we know from our solar system, from the planet-forming disk in our solar system to the distribution of exoplanets, we can infer that the most likely way to form these giant planets is through the core accretion bottom-up model. There are other evidence in the paper that don't have time to discuss, but this is one of them, which I think is important to point out. So now back to this figure, let's look at the smaller population of planets. These are the most common ones. So of course, we would want to know, how do they form? So for that, first, let's look at, again, the occurrence, the true occurrence of planets as a function of distance from the star. Now for the sub-Neptunes, okay? So before we looked at the giants, now we look at the smaller planets. And now there are 4 different curves because we have split our sample in different stellar masses, okay? So here we have the small stars, maybe a third the mass of the sun, and here we have, with G, we have the sun-like stars, and F slightly more massive stars. So what is important here to notice, and it's nicely illustrated by this figure, is that these curves are very similar, right? And so you can actually shift them horizontally and vertically, and you will see that they nicely superimpose on one another. So there is, in fact, a very interesting feature, common feature to all of these curves, which is this turnover in the occurrence of sub-Neptunes planets. In other words, again, like for the giants, if you want, the intrinsic frequency now of sub-Neptunes doesn't always increase with distance from the star, but it plateaus at some point. Now, that's where we make a connection now to the planet-forming disks, because we noticed that this turnover has a certain scaling with the mass of the central star, which is the same as the scaling of the inner edge of the gaseous disk, okay? So there are 2 edges in disks. One is the dust, and the other is the gas. The gas is further in, okay? And we notice that this is the same scaling. Because these planets have a core, right? They are built from rocks of ice or just bare rocks. It's obvious that even though we detect them at this location in the gaseous part of the disk, they could not have formed there. And so this means that migration was an important aspect in leading the planets at where they are. And in fact, if you look into the literature today, there are 2 models, again, out there on how these sub-Neptune's planets could form. One, the migration model, you form your planets beyond the snow line and then you migrate them inward. And the other, the drift model, you bring your building blocks inside the snow line and you form the planets there. It's like if you would build your house somewhere and bring it wherever you want, or you take the bricks somewhere and build your house there. So that's the same parallel. Now, it's interesting that the second model, this drift model, has been also proposed to explain the rocky planets in our solar system very recently. And so one question we had in my group was, can we try to constrain this model? Is there any evidence that these icy pebbles from the outer disk actually significantly drift inward, and then there are enough of them to build the planets in the inner part of these systems? So now we can go back to what I said initially about using different telescopes to probe different parts of these planet-forming disks. And one thing we realized is that we can use millimeter radio observations with the Atacama Large Millimeter Array to probe the icy pebbles in the outer disk. And then we can also use, again, infrared spectroscopy with Spitzer or JWST to probe the water vapor in the inner disk. So this is a very simple and somehow silly animation, but think you have, this is a huge pebble, so a huge icy pebble. This blue thing is the ice around of the pebble itself. And now imagine that pebble drifts significantly inward and passes the snow line. As it passes the snow line, again, the ice evaporates. And so if you have an instrument that can detect that water vapor, then you will be able to inference the presence of that drift. So again, we had essentially to start surveys to measure the amount of pebbles in the outer disk and also the outermost location of icy pebbles. And this is something that we did a few years ago. We observed this star-forming region, the chameleon star-forming region, and we, with the Atacama Large Millimeter Array, we measured the amount of icy pebbles. With the VLT, we measured the properties of the central stars. And so for about hundreds of these planet-forming disks, we know how much pebbles are out there and what is their outermost location. So I'm going to show you just one figure from all these surveys, which is in the paper of my former graduate student, Nathan Handler, which is, I think, a very nice figure. So it summarizes what we know. Each point here is a circumstellar disk around a young star. And for that circumstellar disk, we could measure its size, so the outermost location of the icy pebbles, and also the amount of mass that we have in these pebbles. Here you can see the solar system. That's actually the size of the Kuiper belt in our solar system. And this result is important to place our solar system in context of how that Kuiper belt has been possibly shaped. Don't have time to discuss that. You can ask me in the Q&A if you are interested. But again, this is what we got from this survey. And then together with my former postdoc, Andrea Banzatti, now professor at the University of Texas, we assembled the infrared data to make that connection and answer the question, is there evidence that outer icy pebbles really drift inside the snow line? So the answer is yes, there is a strong hint, and I can show you the reasoning for that in this sketch. So what we observed is that if you see a small disk with the Atacama Large Millimeter Array, so the outermost location of the icy pebble is small, we will see much more water vapor in the inner part of the disk. Again, probably due to this inward drift of the pebbles. And on the contrary, if the disk is large, so the outer pebbles remain outside, we saw much fainter emission in the water. from infrared observations. Then with an undergraduate student here at the University of Arizona, we also showed that, well, while with Spitzer you can detect kind of water lines, things will be way better with James Webb. So here you can see the sharpness of this line increases enormously. So James Webb has a huge potential here to improve knowledge in this direction. And in fact, very recently, there was a press release showing that small disks also have cool water vapor, possibly again due to this inward drift of pebbles, so corroborating our initial statement. All right, so now to the last question. How common are Earth-sized planets? And again, I want to focus here on the question of how common are Earth-sized planets in the habitable zone, because this is going to be important not only for NASA, who is now thinking of building the Habitable Worlds Observatory, a large telescope to detect biosignatures in the future, but also for ground-based telescopes like the Giant Magellan Telescope, which also aim to detect atmospheres of planets, possibly Earth-sized planets. So when I was helping NASA with the mission concept study for what was a predecessor of this telescope, I was intrigued very much by this question, and I wanted to try to answer it myself. So I went back to the Kepler mission. So again, we look at the same plot, planet radius as a function of orbital period. Each dot is a candidate planet. And here there are different boxes, but the important part here is where is the habitable zone in this plot, and that's there, which means that we don't have at the moment any good candidate habitable zone planet, Earth-sized planets to make a statistics. So it also means that if we want to calculate this value, the frequency of Earth-sized planets in the habitable zone, we need to rely on the population of small planets closer in. So we need to extrapolate into that region. And whenever you extrapolate, there are assumptions, there are many uncertainties. And one thing I noticed is that if we exclude the population of small planets inside, for which there are physical reasons to exclude them, then that quantity, the number of Earth-sized planets in the habitable zone, is going to drop significantly. So my student, Galen Bursten, took this problem to the next level. He developed a much more comprehensive model to explain the population of close-in planets and did an extrapolation and came up with a better number. So here is Galen, and these are the frequency of Earth-sized planets in the habitable zone, different values from the past, and this is his value. So the bottom line is that 1 in 10 solar-type stars hosts an Earth-sized planet in the habitable zone, essentially in a zone where liquid water, water can be liquid on the surface of this planet. So this seems like a small number, only 1 out of 10, but we should remember that our galaxy hosts 200 billion stars, of which 20 billion have properties similar to our sun. This means that there are about 2 billion Earth-sized planets in the habitable zone just in our galaxy. And this is why it's worth searching for biosignatures in other planets in our galaxy. So before finishing, I want to acknowledge make a few acknowledgements. First of all, I want to acknowledge the funding agency, NSF and NASA, without which this work would not have been possible. And then I also want to reiterate on the importance of teaching, at least for me. So what I see is that with teaching in the classroom, but also through research, as through the project that I've shown you here, knowledge is not only passed to the next generation, but it is greatly amplified by their contribution. So with that, I want to acknowledge the important role that several senior colleagues had, including my PhD advisor and postdoc advisor, had in my career, and also acknowledge all the talented students and postdocs I had the honor to mentor here at the University of Arizona. So thank you.
Oh, thank you. Thank you for that wonderful talk, Laurie. And I was just thinking, and as you were concluding, the same thing of the passing of knowledge as you demonstrated all the way through in all the students that you had included in the work, and allowed for their graduate theses to learn from you and then build to even higher heights. So thank you for that. Do we have any questions for Lauria in the classroom?
Thank you for a great talk. Could you describe the physical reasons for emitting the close-in planets? And do you have any sense as to why emitting those close-in planets has such a dramatic lever arm on the habitable zone abundance?
Yeah, so I don't have a picture here, but the close-in planets, for the close-in planets, there is this so-called radius valley. In other words, it seems like the planets come in two different beams. They are super Earth, so smaller than 3 Earth radii, and then there is another bump for the so-called sub-Neptunes, right? And so what happens is that from other work that we have done in our group, as well as other people have done, it appears as the population of super Earth here is contaminated by those sub-Neptunes that have lost their atmospheres. So you artificially increase the number of small planets close in. So then if you would, because this process of losing the atmosphere only works close to the star where there is a lot of radiation to remove the atmosphere of those planets, but doesn't occur here, it means that if you include that population, then you would artificially increase the number of Earth-sized planets in the habitable zone. So that is the reason. I hope it was clear.
Other questions from the audience?
Bill? I don't want to be pedantic, but I would like to clarify the meaning of the word pebble, which you use a lot. And is there an agreed upon definition of that term in your community in the scientific sense?
Okay, this is a very good question, which will require some more answers. So it really depends on this dust, right, drifts only at certain sizes depending on their distance. So it's the coupling between the dust and the gas that leads to the inward drift. So it is true that at hundreds of astronomical units is the pebbles, so it's the millimeter, centimeter size grains that drift the most. But once you come closer in, that size is going to be larger. So if you would be around 1 AU, your drifting pebble would be actually a 1 meter size body. So there is not, it would be better to include a more physical approach, right, that takes into account the coupling between the dust and the gas. But at the moment, since our observations are limited to the outer part of the disk, I think it's fair to say that, it's the pebble-sized grains that are drifting inward.
We have a sedimentologist right here in the front row who could also might have an opinion on particle size and names. Any other questions in the audience or online? Amy, do you see anything?
No questions online.
Okay, in the back of it, sure.
Tell us about the Kuiper Belt.
Okay. All right. So let me see. I don't know why I cannot see this anymore.
Yep.
Okay. All right. So Okay, so before this survey that we did with the Atacama Large Millimeter Array, interferometers were sensitive only to the large disks, largest and brightest disks. And so in the community, there was this common statements that the Kuiper belt, so the disk of our solar system, is unusually small, right? And therefore, several hypotheses were put forward as to how you could truncate the outer edge of our solar system early on, right? So this plot shows that is not the case, right? And so the size of the Kuiper belt is within the range of what we observed in low mass star forming regions. So essentially, you don't need these extra processes like, for instance, encounters, or you could have external photoevaporation, now to be a bit more technical, to truncate the outer edge of the solar system. So that's why I think this is important.
But is this figure demonstrating that the Kuiper belt is relatively massive compared to the other members?
Yes,
in this
as
group?
well. So that's another part of the presentation, if you want, which I didn't have time to discuss today. But yes, so there is also a point to make that most likely in these disks, planet formation is already advanced. So that's why we don't see as many pebbles as you would need to form a system like our solar system. Yeah.
What initial condition determines the direction of rotation, this way or this way?
So this is from the initial rotation of the cloud, and it could be, I mean, as far as we know, it can be in different directions, and it's an initial distribution, say, of rotations for the course. Yeah. It's a bit obviously more complicated than what I described here. I mean, there is still a lot of discussion in the community in relation to the importance of the magnetic field that can have on the formation of these disks. But yeah.
Well, you have any last questions? Go ahead.
Yeah, I just wonder the size of these exoplanets. Does that give more information about life on the planet than a small one does, and how there's some kind of life on many of these planets, is what you were saying?
Yeah, so at the moment, we still don't know if these planets have, I mean, if there is life on these planets. We know that some planets are maybe more likely to sustain life because they are at that distance from the star where you could sustain liquid water on their surface. And so those, in fact, are the most interesting planets to follow up, so to have additional observation to search for the presence of the liquid water or possibly the presence of biosignatures in their atmospheres.
Thank you.
And go ahead.
Do you know anything about the burning, maybe meteor that was over Los Angeles a couple nights ago? Broke up into 3 pieces.
I don't
saw
know,
that.
but I'm sure there are other people here in the audience who know more than me on that.
It was quite spectacular. I mean, the photographs. So. No,
Sorry about
said
that.
about what it is or was.
There was a space station battery that crashed into somebody's house in Florida just a few days ago. So, but on that, that last question about life, which is where we're going, the Habitable Worlds Observatory, it's the future of planetary science, and hopefully all of this is going. I'll say thank you again. Let's congratulate